So, I want to talk to you about vector addition and to get across with this animation some of the principles of that, and then we'll move on to doing vector addition by scale drawing and then by calculation. So, what I have here are two vectors, two displacements in this case. See, they're both in terms of distance. So I've got A and B. I can vary the magnitudes of A and B using these sliders. And I can measure or vary the directions of A and B. This is the direction of A, 0 degrees to 90 degrees to 180 degrees to 270 degrees. And likewise with B, I can vary the direction. So, let's imagine that we're talking about starting here and we walk from here to here along A, and then we walk from here to here along B. So you have two displacements, A and B, and the net result of that is you started here and you ended up here. So this is the result or the resultant of those two displacements. Now it doesn't have to be two. You could have any number of displacements adding together in different directions and different sizes to get you from here to here. But what you have achieved with all of these different vectors you might add together is you've got to here from here. So this is the resultant. I'm talking about this in terms of distances, displacements, but it might be forces, it might be velocities, it might be accelerations, it might be any other vector quantity. That is to say, a quantity that has both size or magnitude and direction, unlike a scalar quantity that just has magnitude, for example, energy. So, we are going to be looking in a few minutes at the finding of a resultant vector, the red arrow in this case, by scale drawing of two or more other vectors. So, one of the principles in this is that you draw the vector's nose to tail. So I start here and I go to here. There's the arrowhead of A. Then I stick B on the end of that, and B, this is what B looks like on its own, B then goes here. Now, I could draw B and A, do B and then do A, and the result would be the same because A plus B and B plus A, they are the same. But if I was to draw A like that, and then B on the end of that, I would have a vector that, whilst it is the same size, because the triangle doesn't change, the direction would be wrong. Because this vector runs from bottom left to top right. If I don't draw it right, I'll end up with the right length, and I can find the right angle, but the direction will be wrong. So that will be A plus B. There's B plus A. And you can see that B plus A and A plus B give you exactly the same red arrow in exactly the same place. There's A minus B. So there's A. B runs from left to right. So there's A minus b, so there's a right to left vector with the same angle and the same magnitude, but in the opposite direction. And so a minus b gives me a vector in this direction, whereas a plus b gives me a vector in that direction. A minus b, b minus a. Compare those two. So you see how getting the direction right is important. So in drawing your vectors, and I'll come back to this in a practical sense in a minute or two, it's important that you draw, I'll just get the right one here. You draw your vectors nose to tail, so it is A plus B, or of course, B plus A. Doesn't matter which way around you do that, you'll end up with exactly the same vector. But you draw them nose to tail, so you go, I want A plus B, so there's A. And then I put B in, so the tail of B is on the head of A. And then I draw in my resultant, which goes from where I started to where I finished. So there's the first thing. The second thing is you must draw these the right length. If we are saying, I'll just make this nice and easy to read. If I say that A is 6 meters, then I might draw this 6 centimeters long. And if B is 8 meters, then I might draw this 8 centimeters long. So I'm measuring these. If I'm saying that A is at 45 degrees, then I'm drawing in my horizontal as a dotted line, as a reference line, and I'm measuring 45 degrees from the horizontal. I'm not just guessing, I'm measuring it. And if I'm saying that B is at 100 degrees, likewise, I am drawing in my horizontal and I'm saying 100 degrees. And I'm drawing in my 8 centimeter long line. So it's really important that you do this very, very accurately, because ultimately you're going to measure the length of this line and write that down using your scale. If you said 1 centimeter to 1 meter, you measure this and you say this is 12 centimeters long, therefore it is 12 meters. And you're going to measure the angle between that line and the horizontal and say that's the direction of my resultant displacement in this case. So because you're going to measure what you've drawn and write that down as your answer, if you don't draw it accurately, then your answer could be wrong. It could be outside the accepted tolerance for the exam question. So make sure that you do this really, really carefully.
So, looking at vector addition then, a quick reminder that vectors have magnitude or size and direction. And examples are velocity, displacement, momentum, force. There's lots of examples. Scalars only have magnitude. And examples of that: speed, distance, energy, temperature. So, if we're adding scalars, if we have 5 joules of energy and we gain a further 5 joules of energy, well, we'll have 10 joules of energy. Dead easy. However, with vectors, if you have 5 newtons that way, and you have 3 newtons that way, you have to consider that this 3 is in the opposite direction to the 5, and so you end up with 5 minus 3, which is 2 newtons. So if things get a little bit more complicated and you say, well, my 5 is going this way, and remember that the length of the arrow is an indication of the magnitude of the force, so this arrow should be 60% of the length of that one. And let's say I've got my 5 newtons as I had before, but now I've got my 3 newtons at this angle, which just for now I'll call 30 degrees. We're going to have to be more precise in a minute. So this 3 newtons, that has a little bit of a horizontal effect, and it has a bit of a vertical effect. So we've got a horizontal component of the force and a vertical component of the force making up our 3 newtons. So we have to consider that when we put these two together, some of this is going to make the 5 bigger, and some of it is going to provide a vertical bit the 5 doesn't have right now. So there are 2 ways of doing this. We can do it by calculation, or we can do it by scale drawing. And at GCSE, we do it by scale drawing. So what we would do is we would take some graph paper, and this is where we have to get really precise. We would say, well, we have a 5 centimeter line, 1 newton, 1 centimeter. So we can draw a 5 centimeter line. And there is my 5 newton force. And then I get my protractor. And I said it was at 30 degrees. So if I mark my 30 degree just there, and I go 3 centimeters, from the end of my 5, which is there. Now I have measured that angle to be 30 degrees. So my 5 newtons and my 3 newtons would have the same effect as a single force like that. Now you should be doing this with a sharp pencil. I'm doing it with a pen because it's easier to see on the video. And that line is 7.8 centimeters long, so that I read to be 7.8 newtons. And because it's a vector, I can't quote it unless I quote the direction as well. So now I have to measure my angle. And my angle is 14 degrees. So my resultant is 7.8 newtons. And you might say, well, I only had this and this to 1 sig fig, so that is 8 newtons at an angle of 14 degrees to the 5 Newton. And that is my answer. Now notice that I drew the 5 Newton and then I drew the 3 Newton nose to tail with that. So I started and I went this far with the 5 Newton, and then I said, well, I've got a 3 Newton in this direction to add, so I started the back of my 3 Newton here, so that I start here and I end up at the end of the last force or velocity or acceleration vector, whatever the vectors are. And my resultant then goes from where I started to where I finished. So that's how to do that. Now, let's take an example. Let's say a Tesla car, Model S, has a force of 100 kilonewton, 100,000 newtons applied by the motors horizontally forwards. Let's say we have frictional forces of let's say 10,000 newtons acting horizontally backwards. And air resistance, and I'm only going to consider the air resistance acting on the windscreen at this point. Just to make things simple, give us a nice easy angle to work with. $60 degrees to the horizontal, and 20 kilonewtons. And the first thing we want to do is to calculate the resultant force horizontally. So we have ten kilonewtons reducing the 100 kilonewtons that we had before. So we have 100 minus 10 is 90 kilonewtons due to the motors and friction. And we have a force of 20 kilonewtons, a 60 degrees to that. So if you just sort of sketch that out, you've got a force like this of 90 kilonewtons and a force like this of 20 kilonewtons, and that's 60 degrees. That's kind of the way I'm thinking, but now I have to draw it properly. So I'm going to say 9 centimeters, so 1 centimeter to 10 kilonewtons. So let's do that. So if I go 9 centimeters. To there. There we have our horizontal force. And we also have a downwards force. Let me just rearrange this now. I've done that wrong. I need my 9 there, because I haven't got space to draw the So there's my 9. And now I'm going to come in and say I want a force at 60 degrees to that. So there's 60 degrees there. And I want 2 centimeters. So if I put the 12 centimeter mark on the end, and I come down to the 10 centimeter mark there. So there I have my 20 kilonewtons, and that's my angle of 60 degrees. So my resultant then, going from where I started to where I finished, that's 8.3 centimeters long. So that's 83 kilonewtons. That was 90 kilonewtons. And then all I have to do is to measure my angle. And my angle is exactly 10 degrees. No, it's not. It's exactly 12 degrees. So I have a resultant of 83 kilonewtons at an angle 12 degrees to the 90 or 12 degrees below the horizontal.